The course is going to be based on Geometry Gym tools. I have been using Geometry Gym tools since many years. I was still in Rome at that time. And I got an email soon after I wrote the email last night with the reminder of today's session. An email from a participant that was asking about other tools that we have available in Grasshopper for the Grasshopper to Revit interoperability. So you might know that there are, well, many tools available. If you go and browse in Food for Rhino website, you will see that there are plenty of plugins. The reason why I focused on Geometry Gym since the very beginning, actually there were no many tools available at that time, but I like the focus of Geometry Gym tools. The Geometry Gym is actually a private company run by John Mirchin. John is a complex professional because he's a computer scientist and also a civil engineer. So he has all the features to clearly understand what are the problems of this interoperability challenge that we have. I like the way that he solved or tries to solve the problem. Also consider that John is basically he's behind the development of the IFC exchange format. So he doesn't have just the geometry focus on this interoperability question. So, for example, as Soto was saying, the interoperability between Grasshopper and ArchiCAD is more focused on the bringing Rhino geometry inside ArchiCAD. But it's very limited as regards documentation. Geometry Gym approach is the opposite. So Geometry Gym objects that we are going to use allow to create native Revit elements from Grasshopper. So when you export them inside Revit, Revit is capable of recognizing everything of the geometry that it's receiving, not only the geometrical part, but also the documentation part or non-geometrical information. Okay, so that's why I like the Geometry Gym approach. Honestly, I also have to, well, I don't get any percentage from Geometry Gym, of course, but so I must be honest. Geometry Gym tools are always a work in progress. And that's because the tools that we are considering, like Rhino, Grasshopper, and Revit itself, especially Revit itself, as you know, Autodesk always publish some new versions each year, so they are a constant work in progress themselves. So Geometry Gym tools are constantly updated. I would say on a monthly basis you have something new coming up from Geometry Gym. So there are some things that that should also, let's say, work with some problems from time to time. For example, while preparing this workshop, I'm still having a problem with the shaft and openings, vertical openings in the floors. But this is something that the advantage of working with John and Geometry Gym is that it's a very small company. So you write down an email and they reply in no time, and they fix the problem in no time. So they're very open to fix this kind of little bugs. But in general, it's a very stable and reliable tool. So that's the reason why I will be focusing on Geometry Gym. Geometry, you should have installed all the plugins and software setup that I was recommending inside the course page. As regards the recommended Grasshopper plugins that you might have seen in my blog, it's a huge list. I understand it's a huge list of Grasshopper plugins. Probably those who are more into Grasshopper have those plugins and more. So in my case, you can see, for example, that if I expand Grasshopper, there is no room for seeing any of the titles of these tabs because of the quantity, the amount of plugins that I have installed. Actually, I should remove something because it's beginning to be too crowded, this toolbar. So it's very common for those who make a complex use of Grasshopper to have a huge amount of plugins installed. I do recommend that you install at least those recommended plugins, because with those plugins you can do basically whatever you want in Grasshopper. Another doubt that you might have in terms of why we are using this workflow, for example, why don't we concentrate on using a dynamo directly inside Revit instead of using Grasshopper and worrying about the interoperability? There are two reasons. Okay, and the first one is not Rhino inside Revit. So you might think, okay, so Rhino inside Revit is going to solve any interoperability problem, which is somehow true. Okay, so with Rhino 7 coming out, there will be a huge step forward, both in the interoperability aspect between Rhino and Revit, but also from another point of view that has nothing to do with our topics today, which is the mesh management in Rhino. So it's going to be something very interesting, Rhino 7. But the main reason, because we are focusing on Rhino Grasshopper to Revit, is because Rhino geometry library is way richer than Revit geometry library. So in the end, Revit is always an Autodesk product, which is still based on standard, let's say, solid modeling. Okay, while Rhino is a NURBS modeler. So Rhino geometry library is way more rich than Revit geometry library. And actually, this is there are pros and cons, of course. So there are some limitations in this workflow that cannot be solved, not because you cannot do things in Rhino Grasshopper, but because Revit is not capable of fully understanding what Rhino is saying. Okay, so they speak a different language, so never forget about this. The IFC is the dictionary that that Revit and Rhino use in order to understand each other. Okay. IFC itself is another work in progress, and IFC is not only about Rhino to Revit interoperability. IFC is an exchange format that allows CAD software to communicate with BIM software, whatever they are. So you might want to use GSA, Robot, Revit, Tekla, whatever BIM software you are going to use in your workflow, be it an architectural BIM, a structural BIM, or something more, even more specific, like structural analysis or whatever. And IFC in that case is the exchange format. And IFC is a work in progress because there are several versions. Actually, there is another version which is about to be released. We are working actually with IFC 4. The previous version of IFC was called, don't ask me why it was called like this, but it was called IFC 3x2. So I don't know why. It could have been IFC 6, whatever, but they called it 3x2. The huge implementation that they did with IFC 4 is that IFC 3x2 was more about coordination. So it was only a geometric conversion tool, basically. So you could export, for example, Rhino geometry into Revit architecture. The problem with that is that as Revit doesn't understand NURBS objects, what happened is that if you in Rhino draw a box, so a box in Rhino is an extrusion, right? So it's a solid primitive. Revit can understand this kind of object, okay? And so it was imported in Revit with the same properties as in Rhino. But if in Rhino you can also create something like, I don't know, something like this. So this object here is no longer a sphere because I rebuilt this with several control points and degree 3 and so on, so I can deform it organically. And now Revit cannot understand these kind of things. So with the IFC 3x2, what Revit got was a mesh representation of this thing here, which was a weird object made up of several hundreds of triangles or quads or whatever, just a simple NURBS to mesh conversion. Okay, IFC4 is capable of taking this geometry and bringing it inside Revit with the same properties that you have here in Rhino. So it's a huge step forward in terms of geometry conversion. And also FC4 is capable of transmitting and transferring non-geometrical information. So yes, that's the big leap that we have with IFC4. Now, of course, we are going to concentrate on IFC4 just so that you see there is an option where we are going to bake things or export things from Grasshopper to file in this case, where you can select the IFC version, you see. And there are also other options that you have inside these export tools here, like if you want to also export some CAD version of your model, but we will discuss this later on. So yeah, basically that's the reason why I prefer to use geometry gym tools. So this is what we are going to have available. The software setup that you see, it's the huge amount of plugins that we have here, but when you install geometry gym tools, you will have mainly two toolbars in our case, because if you install all the geometry gym tools, you will have plenty of stuff in your interface, but in general, there are basically this is called basically the Revit, the Geometry Gym Revit toolbar, which is the one that we are going to use most of the time. But there is also, you see that the advantages of having a clean interface is that you can easily find things when you need them. So yeah, it's this one, Geometry Gym IFC. This is the general version of Geometry Gym tools. So in case you are more interested in exporting I would say a neutral IFC format, so not depending on a specific receiving software, you can also use the Geometry Gym IFC. Of course, if you switch to the Geometry Gym Revit, you will find the specific workflow that we are going to use. There is also Bull-Ant. Bull-Ant is another part of Geometry Gym tools, which is a plugin that has some geometric utilities and so on. And we are not going to use that plugin too much. And also there is, in Rhino, you see that there are some geometry gym tools and also toolbars that are added, but we are not going to run into these comments here. We are going to concentrate on Grasshopper to Revit interoperability. So all the rest is basically a standard Grasshopper workflow or other plugins. I will point out which plugins we are using, and I also will, as I will be sending you and sharing with you this definition from Grasshopper, I will also place a small note wherever a particular plugin is being used, so you know that this definition, in order to work, it needs a specific set of plugins. Okay, so let's start. Let's start with very basic things. I created here a group which is called warm up. So in this group, we are going to see the basics, the very basics of Geometry Gym tools. One recommendation, one very important recommendation. There are the IFC, basically the IFC export, as well as, so of course this is pretty obvious, but as everything here is based on IFC, the encoding of the IFC properties depends on the Rhino document units. I do recommend that you pay attention to this thing here. I'm going to close this file. I'm going to go here in Rhino. I don't want to change anything. This is a blank template that I am using, and I'm going to work with millimeters in this moment. Okay, so if I open this file and I browse here and I turn on this, you see that there are some things that look exactly the same. Okay, but if you are working with a millimeter template and you open some workflow which are more complex, like for example in this case, I'm not doing because this could also hang to Grasshopper. the IFC encoding here and the implementation of this workflow, which creates several things like columns, beams, and floors, and walls, and truss system, and many things. We'll read the information in this document in millimeters. So basically, the model will be scaled up like in a huge preview. And this can also hang Grasshopper because of the graphic card capabilities. So pay attention. Always, first of all, start your Rhino with some meter, large object meters. Eventually, this is the standard for architectural design at the building level. And then you open your Grasshopper definition. Okay, so just so that that you know what happens when you see something weird happening, it's because of the scaling of the units that you're using in your Rhino document. So let's concentrate on this first thing in order to understand how things work in geometry gym tools. So the goal here is to build a grid system, as you can see, grid lines. There are grid lines, and there are also columns. Okay, some specific column type with a specific profile that we are going to study here in this definition. So the main goal is to create these things here: Revit grids in the two directions, and Revit column, which are these these steel column profiles here that you see. So these are the things that are going to be passed to Revit. Okay, but in order to get to this point here, you must build all the properties of these objects here. Now, let's concentrate on the simple things. Revit grids. Okay. First of all, you need to define the grid lines in two directions, or at least two directions. Now, these directions can be whatever. So I'm going to, as I did also in previous workshop, and as I do normally, in order to perfectly understand the workflow, I will also recreate these things from scratch so that you can see what's the proper way of defining things. I will not necessarily mimic the way that I build things in this preset definition, so you will get the point of working with this type of things. So let me turn off this thing here. I'm going to take a simple line container, and I'm going to the top viewport. I don't care about 3 dimensions right now. So let's set multiple lines. So I'm going to define like this and this and this. I am drawing this line like in a non-parallel fashion, just on purpose. And these are going to be 3 vertical grid lines, so oriented more or less along the y direction. And then I'm going to take another line container and set multiple lines and draw the x-aligned grid lines. So we are not talking necessarily about a rectangular grid. Okay, of course, in the real life, in practice, you will be eventually using regular grid lines. So probably you will be working with this kind of grids, like radial grids or rectangular grids or square grids or whatever, right? But in order to understand that there is no limitation in this sense, you can use whatever set of lines that you might want. And so these are very simple geometry. You go directly in Geometry Gym Revit, and you have the Geometry Gym Revit grid. This is actually somehow a generic toolbar, generic set of components where you find some libraries, some stock material, and also this kind of very simple object like the Revit grid. So it asks only for 2 parameters. Actually, I'm going to need 2 of them, one for the vertical lines and one for the horizontal line. So the curves that I want to convert in Revit grid are these. So it's pretty straightforward, right? And you also must give a grid name. So let's use a smart way of naming these grid lines. So I will be using, for example, letters for the vertical lines and number for the horizontal line. And so I'm going to take a chart sequence, which asks for how many, well, names you want to give to these grids, basically, and the amount of characters that are going to be output from this depends on the amount of lines. So I'm going to list length this. By the way, you see that normally I use shortcuts to write down these functions or components, or do you want to call, or nodes that you want to call them. If you want to define this kind of shortcuts, which is something very useful, you can, for example, in this case, like list length, if you go inside the set component and you go into list, you have this list length. Right click on it, component alias, and you define the shortcut that you want to use. Like in my case, LL, list length. Okay, and you can do this with whatever type, with whatever command you might want to run. So list length is actually telling us how many vertical lines we have, 3, and this is the count for our chart sequence. So we have A, B, C. This is going to be the grid name. You see that it's a text. So the component is asking for a text. And so we have this. It's already defined. You don't see anything in the preview. So if you want to have a visual correspondence between what happens in Rhino, then if you want to see what happens in Rhino with the same preview that you get in Revit, in this case, the GG Revit grid doesn't show any tag with correspondence to the grid elements, but you can simply add a text tag, whatever, 3D or normal, and we can also create, for example, the endpoints of this, and you can place these things, well, basically whatever you want. So in this case, you see that we are already getting this kind of, well, you can do this with a more pleasant aspect. You can also create like bubbles, like in Revit if you want, aligned with these grid lines, but this is just, let's say, manual work here in Grasshopper. So I'm not going to go through these particular things, but aesthetically you can do whatever you want also in Grasshopper. So basically, if you want, you have also tagging in Grasshopper, which corresponds to what you will be getting in Revit. But the important thing is not this, is this one. So normally, in order to concentrate on Revit stuff or things that are going to be exported to Revit, I normally take the final element, group it somehow, and give this a specific color, something that makes it recognizable, normally a bright green, which is something very visible. And when I need to identify other things that must be exported to Revit, I simply select this, right-click on the group, and select the option Add to Group. And normally, I give this group a rectangle outline in order for these things to be kept separated inside Grasshopper definition. So every time you see a green thing here, is a Grasshopper object that are going to be exported to Revit. Eventually, in the end, we are going to reorganize this definition in order to have a clearer approach to what we want to export or not. But nevertheless, let's concentrate on this. So we must do the same for the other grid line set. So I'm going to simply copy this and plug the new lines wherever they are connected. So in this case, I don't want to use a chart sequence. I want to use simply a series. So the count is going to be the list length, and the series is going to be give us the number for our grid line. If you don't want line number 0, you just set the start value to 1, and that's it. And so now, if we take a look at this, of course, we must pass this series here. Now, these are numbers. Okay, this is asking for a text parameter. Nevertheless, if you connect this, it will interpret the values that it's getting as text. Of course, text is not capable of recognizing this as a number eventually with decimal or whatever. You see that series can output a 0.1, which is floating point numbers. In this case, it's outputting only integer number, but this will be interpreted like text. Okay, and so we have this grid system that we can basically already use for our Revit, or sorry, Grasshopper to Revit workflow. One thing that I would say about this is that normally grid lines are basically a secondary aspect with respect to the physical position of structural elements. So we use, for example, grid lines in Revit in order to define the position for, I don't know, structural columns and therefore also architectural columns and so on. So normally you shouldn't work directly with grid lines like we are doing right now. Eventually, we can start this kind of process by using or by placing columns at the right position. In that case, you might want to use the another method. So, for example, let's say that I want to place columns in a very specific position. So I'm going also to give you a different approach to the same problem. So let's say we want to place this column with a span of 10 meters, like I'm doing right now, like this. So I don't care about drawing the structure, the grid lines at first. I only have the position of these things here. How do I derive this grid line starting from this structure? Well, the easiest way of doing this is creating something like interconnections. There are several ways of creating interconnections between points in Grasshopper. Eventually, you might know the mesh triangulation methods like Delaunay edges, but in this case, I would not recommend it because it interconnects everything with everything, so you get also diagonals. Okay, but as diagonals are larger than normal horizontal vertical lines, you might want to use some other components like this, which is Incestus Network from Heteropera plugin. I don't know if you are familiar with this plugin, but it's a very useful one. So it's one of the recommended plugins in my personal list. So if you do this, things get worse because you have all the possible interconnections because you're not defining the number of interconnections and the distance. So in our case, what's the maximum number of interconnections that we want? Is 3 for these mid columns here. So we can already set this to 3, but if you are considering also another structural line here, you will have 4 connections as the maximum. So let's limit this to the maximum amount of connection that we have in our model. And also let's limit the distance, because in this case we have a 10-meter span between the columns. So if I set this to 10.00, you see that the connection scheme changes and we get rid of the diagonal interconnections. So with this, you can control things a little better than with the Delaunay interconnection method. Okay, and there are also other methods that you might want to use. You can do, for example, a more specific manipulation, like isolating the points by row and then creating transversal connection and longitudinal connection. So if we have this point, you can deconstruct the point. This is the only moment when I'm going to concentrate on the Grasshopper workflow. Okay, so I suppose that you can come up with several solutions. But in this case, for example, I want to separate the columns by the y coordinate. So I need to concentrate on this thing here. We are only going to get 2 values. Okay, so we can say that if we want to separate these points by rows, we can consider the y component. So you see that we only have 20 and 30. So if the point has a y coordinate, which is 20, it will be stored in a group. And if it has 30, it will be stored in another group. So you will have 2 lines of points. And you can do whatever you want. Create a polyline, for example, horizontally, and cross sections like in the transversal direction. And you come up with the same thing. But once you have this, you have this set of lines here.
Marco?
Yes, tell me.
What is the name of the plugin of the Incestus network?
Yes, it's called Heteropera. Sorry, Heteropera. Yes, I will leave it like this. And it's very useful. And also it allows creating some smart management of randomness in Grasshopper. You might know that Grasshopper, well, is not that good in handling some random magnitudes or values. So Heteropera adds also this kind of possibilities in Grasshopper. So you can come up with a grid with whatever type of workflow you might want to use. But in this case, I will leave this like a reminder. Once you have the connections, I would suggest eventually you extend curves. So you have the original line starting from one column and reaching the opposite column, and then you extend this curve at start and end in order to have a larger representation and convert that curve into a grid line. You will have this kind of approach inside our preset definitions. So I'm not going to insist on this, but you can come up with whatever method you might want. But the approach in Geometry Gym is always like this. You have a Revit entity, like the grid line in this case, and you must feed this component, this node, with all the features that Revit requires in order to understand what you are going to send to the software. Okay, so grid line is the easiest element probably because it only has a geometry and a well tag or label or whatever you might want to call it. Okay, so it's very simple. Let me move this here. Let me group all of this together like this. So grid lines is pretty straightforward. Now the columns. Oh, well, let's concentrate on this a little more. So we will have also another interesting feature. So for example, we have this set of lines and this set of lines, and we want to place columns at the intersections, like you would do in Revit. Okay. There are several types of intersection that Grasshopper can calculate. We are interested into physical intersection because we have physical line intersecting other physical lines. So we go into physical, curve to curve, and you have curve A and curve B. If you do this like with a list, you will see that this is the longest list method acting inside Grasshopper. So you have this kind of strange intersection scheme. But if you graft one of the two inputs, you will have all the possible intersections between the two sets of lines. And so we already have the points, which are 6 available intersections. So what we want to do next is go into our, let's see if it's visible. No, it's no longer visible. Our Revit toolbar, and start considering placing columns, physical columns at the intersection of these grid lines. I suggest you start from the end, at least at the beginning. You start with the end nodes, because it's easier to populate or to feed those nodes or such nodes with all the necessary parameters that Revit asks for. So for example, like you would do in Revit, when you want to place a column in Revit, you don't place directly the instance of the column. Well, of course you place the instance, but in order to place the right instance, you must decide what family or what type of column you are going to use, right? And the type of column contains a whole set of properties, which are like, for example, material, manufacturer, cost, and so on. Okay, so if we start from the end point here in Grasshopper, it's a little clearer, especially when you start working with this tool, what you must implement, what it's mandatory to implement. Okay, so you see that here you have two groups besides the GG Revit. You have GG Revit element type, which is basically the type or the family if you want, and the GG Revit instance, which is the final element that you want to physically place inside your 3D model. So I would suggest in this case that we start from the instance. Okay, it's the instance that is going to tell us what it needs in order to work. And we simply take GG Revit column. Now, one consideration, GG Revit column, even if you will see that there is an option for defining a non-structural column. Geometry Gym tools are not optimized for the architectural use of Revit. They're optimized for the structural use of Revit. Actually, I already discussed this with John, and he says he's going to implement the architectural column, which is just some switch in his mind, I'm sure. So it's going to be pretty quick as a process for him. But keep in mind that we are going to see columns from the structural point of view for now. Okay, at some point, you will see that there is a switch, and this switch will become effective in the next future. Let me move these additional things down a little, so we have more room for our introductory things. So this column instance is asking for a series of things. And the first one is the column type. So you go in the other group, and you will find that there is a ggRevit column type. Okay. And of course, this is pretty straightforward. Okay, so you plug the column type in the column type input in the instance column. Okay, so let's move to the column type, and you will have a series of things that you must do in order to. This is not, let's say, for Grasshopper. This is for Revit. In order for Revit to understand clearly what it's going to receive, you must fill all the necessary inputs in this column type node. So the name can be whatever you want. Now this is interesting because another implementation that I asked John like recently is that when you import, this is actually something that should already work like this, but there are some flaws in this process. If you use as a name that is already present or loaded inside the Revit project, like as a family, then Revit should place exactly this component or this element that is arriving from the import process inside the right family. So Revit is capable of recognizing the family if you give the proper name to this column type, for example. But nevertheless, I will start using some dummy names, like, I don't know, something like column family. This is going to be the name of this column type. Revit profile is something that you can provide in different ways. For now, I'm going to stick with a very stupid profile, like rectangular profile, something like this. The main aspect that you can already see is that there are plenty of inputs inside these components, and this is because Revit objects are filled with parameters. So this is exactly what you have inside Revit. So that's why I consider this probably the best approach to the Rhino to Revit interoperability. So once again, you have the Revit profile component, you have the name. So I will copy this and take this like profile name, plug it here, and you have the geometrical aspects. Now remember that you are drawing in meters. Okay, I do recommend that you work in meters. Actually, you will see that in Revit, I will be starting a new project with a custom template which is already set in to work in meters. Okay, I do recommend you do this because normally, as we are discussing interoperability from Grasshopper to Revit, so you might want to use whatever type of units you are basically you feel comfortable. You can work in centimeters or in light years, I don't know. Okay, the important thing is that you have the same unit in both in Rhino and in Revit file. But if you consider a wider range of interoperability, like for example structural analysis software and so on, it's recommendable that you work in meters. In our case, we are going to define the depth of this column like something between more or less like 50 centimeters, which is 0.5 meters. So I'm going to give, well, I want square columns. So I will use these as depth and width. You see that it already turns gray because it already has the necessary parameters that it needs to work. Okay. Then you have the thickness of the wall. So you see that if this profile is this parameter is set to 0, you will have a solid square cross section. So it's not hollow, as you can see in this icon here, because I'm not considering a thickness for the wall. Okay, so you might want to give this, for example, few centimeters, like something like this, 5 centimeters thickness for this wall, and you will have a hollow section in this case. And you will also have like the possibility to fillet the corners of this cross section if you want, but this is just other parameters, you know, it's just numbers. You can do this however you please. Just in order to better understand what this thing is doing here, this is the first well, actually, it's not the first IFC that we implement. There are also the grid lines. You can see that everything is translated into IFC objects or parameters. So as John says himself, these tools are nothing more than a dictionary that takes Rhino things and convert them into IFC words, something that Revit can understand. Okay, so you see that here you have the IFC names for grid axis, which is IFC grid axis, and then there are some parameters like the number. You see that here is based on the series, so you see the number. If we take the other one, you will see that there is A, B, and C, and there is a progressive number, which is a unique number, and so on. Other IFC properties. There are many things that happens inside this encoding that are not always clearly understandable, but they are all stored inside the IFC export. So even if in Grasshopper workflow you are used to have this node is actually feeding this one, which is feeding this one. So for you, for us in Grasshopper, the important node is this one. But for Revit, they are all important because each one is defining an IFC property. So everything here is going to be exported in the IFC file that Revit can read and rebuild the profile, the column type, and the column instance. Okay, so everything here will be stored inside the IFC export. And this is already working, so you already have defined the proper profile. So column type, we still miss the material. Material is another mandatory parameter that you must set for a type of element. So we go once again in the general set of components, and you see that there is a Revit material layer, Revit material. We plug this into Revit material, and we must define the material. So let's take another panel. Let's call this, I don't know, my material. We will give proper names to these things later on. And you see that we already have these things working, at least down to the column type level, because we still miss something here, which is basically the geometrical aspect. So everything here is non-geometrical information. Okay, so we are already defining the non-geometrical information, which is something fundamental because Revit can use this for, well, documentation. So actually, you can create schedules and quantities, and you can, for example, estimate the costs and whatever. Okay, so everything is based on these steps here, not only the geometrical aspect, which is the last one. So for example, here I would say that this Revit material, which is my material, if we are using a solid, a hollow section, probably this is going to be a metal column, right? So in this case, I would eventually focus on the class of this material. You see that there are a preset categories of material. One of them is metal. This is one thing that actually I would eventually place a note here. Define material class. Okay, so this is somehow important because this allows Revit to perfectly understand what type of material you are defining. As this is a custom material, because you are defining this by all the parameters. Okay, so my material is not clearly a metal. You can name this like, for example, steel, structural steel, aluminum, or whatever you want, but it's just a tag. It's a text. It has no meaning in terms of material definition. So you must define what type of material you are defining here. And so I will switch this to metal in this case. Okay, you do this once. You can also create a value list in order to have it available whenever. So you must replicate this kind of thing. Remember that there is also a tip here. You see that 0 is ceramic, 1 is concrete, 2 is earth, gas, generic, and whatever. You see here there is gas as well. It's because this material here is not a material for columns. It belongs to the generic group of nodes. So this material can be used for defining, for example, the I don't know, insulating layer inside the wall, which can be air or any gas if you have some specialty equipment, for example. So it's not specific for columns. Okay, so that's why you have this wide range of material types, including textile, which is something that you wouldn't use for defining a column material, right? But this is a generic material definition. So that's why you have this class. Pay attention to it because it's mandatory to define this correctly, else you will have some misbehavior in Revit. Okay. So we have some nice column type which has a square profile and it's made up of metal, like any metal that you might want to implement. So column type is working properly. The Revit column is not yet properly defined because it misses the axis. And the axis, you can see from the black icon, is a line. Now, we only have the intersection points, okay? And we must create the columns by line. So the easiest way, and probably the more practical and the closest to real life, is to create, for example, a line SDL starting from the intersections along the Z direction, which is already a preset in this direction input, and just defining the length. So if you want, for example, a length of 3.5, you just define this as the length of your columns, and then you plug the axis in the axis input. And you already see the columns appearing here. They should be hollow. Yes, they are. There is no fillet in the corners because we didn't feed the outer fillet and inner fillet of these columns. But if you do, you can have a fillet, for example, of 1 centimeter for the output and something like 5 millimeters for the inner fillet. So you would see that we should already get some filleting here. Oh, maybe, yeah, sure. I am working with large object in meters. Remember that everything depends on the units. So if you go into this template and you take a look at the unit settings, you will see that the absolute tolerance goes down to 0.01. So in this moment, this is not capable of understanding a inner fillet of 5 millimeters. Okay, so that's why you see no difference here in the inner corner of these columns. Okay, but if I take this, for example, to 0.02 for the outer fillet and 0.01 for the inner fillet, you should, yeah, exactly. We have this nice fillet column cross section here. Okay, and this is interesting because this is something that, well, normally the question that I get at this point, that I receive at this point, is this okay? But I can do this already in Revit. Of course, in Revit you have the same type of behavior. Like for example, if I go back to our, I don't know, vertical lines, okay, and I take this and say set multiple lines and take 1, 2, 3, 4, and 5. I have this kind of automatic cross-section, well, grid lines definition, cross-section, intersection point definition, and the columns are built exactly at the intersection between the grid lines, which is something that you already have in Revit, but not like this. Not like with this, let's say, smooth workflow. You must do you must perform more steps in Revit in order to get to this automatic connection. Okay. Also, we will see that this has also consequences when we will switch to Rhino inside Revit. Okay, we will see that this method is still absolutely valid even if you are running Rhino inside Revit. Okay, so this workflow will be valid also in Rhino 7. Okay, so that's why we are focusing on this. So yeah, basically this is how you define the columns with a standard profile. But if you go inside GG Revit, you see that there are also other presets. You see, for example, C profile definition, a circle profile, I profile, T profile, and so on. There are also some, this works exactly like the one that we have used right now. So this is a standard rectangular profile that you can customize in order to be square, rectangular, solid, or hollow. Okay, and they work exactly the same. Well, of course, the circle profile can be solid or hollow. The I profile can only be I profile, C profile, and T profile. They work exactly like this. There is an error in the icon, but nevertheless, you get the point. Okay, and then there are some particularly interesting profiles, like for example, the GG Revit profile. Let's grab this and have a look at this. You see that it doesn't ask for almost anything. It only asks for the name and the profile. Now the profile is going to be a curve. You see, it's a curve or a planar B-rep face or string, but normally you define the profile by curve. Not you don't use a B-rep face. You should be crazy enough to create a B-rep in order to use only a face. But anyway, the profile is defined by a curve. So, for example, if I want to use something like, let's create a small rectangle, like measuring 1 by 1. Let's rebuild this with 8 control points. And I want to use this as the cross section of my column, like this. Okay, so I import it. Set one curve, it's going to be this one. Let's internalize it so we get rid of Rhino geometry. I want to keep the Grasshopper definition independent from Rhino file, so I can share just the Grasshopper definition. So this is going to be the profile, and the name is going to be strange profile, of course. I see no other name for this kind of section. You see that the profile is already defined, and you can take this and replace the actual Revit profile that we are using for our column. So you see that you have this thing here. Now, when you define the profile, you see that the columns get shifted, because if you define the profile in this point here, the actual center of the profile is not the center of the curve that you have designed, is the origin of the coordinate system. So you might want to take this curve, well, let's undo deleting. And I'm going to take, for example, a line from quad to quad, and I'm going to move this from this point to 0. And so I'm setting one curve again, which is going to be this one, and internalize data. So I'm working with this. And you see that now columns are displayed correctly. You see this kind of fancy column. The reason why you could eventually use a B-rep face, planar face, is because with this method you can only define solid cross section. Okay, but if, for example, I take this curve again, and I create, for example, a circle in 0, something like this, and then I create a planar surface from these 2 curves. This is a surface, basically. I can import this in Grasshopper with many parameter. Here, I'm going to use first one. Set one B-rep is going to be this. Let's internalize data. And if I do this, you get hollow section. Of course, you can define whatever type of hollow section, not this weird cross section here. But anyway, you get the point of how this thing works. The Revit profile has this preview here. You can hide it if you don't want to see it. But the important thing are finally the columns. So you can define the column profile also with a custom profile. I will leave this eventually here, like here. So we have 2 different ways in this moment, but I'm going to show you a third one. This is going to be by catalog. So there is also in GG Revit a catalog profile definition, which is this one. This is interesting because this is already a huge catalog of cross section divided by, well, continent, or, well, normally the standard profiles that are used inside a specific geographic area. Okay, so you have all the profiles already encoded in this catalog. And the interesting thing is that this catalog corresponds exactly to the catalog that you find in Revit. So, of course, I repeat, this is for structural column definition. So you will only find, well, actually right-click on this, and you will see, for example, that there are, for example, I don't know, IPE beams, and you will see only IPE beams. It's difficult here to find structural beams, for example, or structural columns that are, or sorry, architectural column, because they are not implemented for, this is not implemented for this reason, okay? But nevertheless, it's quite useful. So in this case, it's way easier. You must simply plug the catalog inside the Revit profile, and automatically you get, in this case, we get IPE 100, which is basically a beam. It's improper to use it as a column, but if you go here, you will see that your profile, you will also have columns. So just switch to the desired profile, and here you have your columns, okay? So probably this is the easiest way of defining a Revit column profile, or beam profile, but you know, it's limited to this kind of structural profiles. If you want to define something original, you can define it, for example, by profile here or by standard profiles. One consideration, remember, and this is not for Grasshopper use, this is for Revit. When you define a structural column, remember that in Revit, structural column, they don't blend with, for example, architectural elements. So once you have, well, let me show you the file that I already prepared. This is a glimpse to what we are going to find later on. You see that we have a structural column here, and this is not blending with the wall, of course, because they have different functions. So another interesting profile as regard columns is the tapered profile. I'm going to insert this here because it's quite nice to play with it. So if you go inside the Revit stock things here, you have the tapered profile. And the tapered profile only asks for two profiles, like the starting and ending profile. So I'm going to use, for example, the catalog in this case. I don't want to work with many parameters, and also to keep the definition like a little clean without having many wires. So I'm going to use the HT 320 by 127. And I'm going to copy this and use, it was your profile and it was HT columns. So I'm going to take 320. This is the one that I am already using. And I'm going to use this, which is more or less half the height. So if I plug this here and this here, I'm creating a sweeping profile, basically. So if I do this and change the Revit profile, eventually in this case, I think we have some misbehavior because of the thickness of the elements, maybe. Well, actually, you see that there is already the cross section is basically reducing its height. So this is basically a diagonal face in this extrusion, in this sweep for this column. Okay. Of course, you cannot use completely different profiles in this case, because you will have a weird behavior, of course. But in this case, you can use this kind of. Let me see if from the right view we can clearly see this. There is this kind of little step here, which is telling us that the face has some inclination, but it's a very little effect. Eventually, we can see this by defining shorter columns, something like this. This should make it clearer. Yeah, you see that we have this inclination for the outer face along the height of these columns. Okay, but anyway, with this thing, you can create a tapered profile for tapered column for your project. So this is regarding the profiles. Another thing that you can do, for example, and this is interesting working with Grasshopper, you can take advantage of Well, actually, whatever type of technique that you might want to use for defining, for example, in this case, the column orientation. Now we are working with vertical columns, but the orientation of the columns is basically defined by the SDL line. Okay, so for example, if I take a point and I set one point, place this point, for example, here, and move it up like this, and then we have the intersection point and this point. So if I define a vector 2 points, starting from the intersection point and going towards the attractor point, we can name it like attractor point, we will have these 10 intersection actually, 10 vectors, all pointing towards this point here. We can unitize this in order to have some one length vectors, and then we can define the amplitude for this with exactly the same slider. This is not properly correct. I'm going to discuss this in a few seconds. But if I take this as, direction of the SDL line, we will have this kind of columns that are basically have some inclination pointing towards this attractor point here. Of course, this kind of process was, as some structural consideration, brings some structural consideration. Actually, during the import in Revit, if structural elements have some kind of weird inclination, the import process asks if you want to give these elements some structural support. Okay, so as this workflow allows basically creating whatever type of architecture you might want to create, there must be some kind of double check from a structural point of view. So remember that geometry gym tools are created with an eye to structural design. So it's nice to have that kind of double check as regards the structural behavior of what you are drawing. But anyway, you can come up with whatever technique you might want to use in Grasshopper to define this kind of aspect. Why I was saying that this is not exactly the proper approach, because if you define the length of these columns by a specific length, like 5 meters in this case, due to the different inclination that we have, not all the columns will reach the same height. So as we are also going to create levels for our building, we must tweak this in order for these columns to reach all the next level as an extension, okay, for the structural elements. And so in order to handle this properly, what I'm going to do right now, I'm going to define also Revit levels. We go inside the DG Revit group. Remember that all the generic aspects are defined inside this group of comments, and you will see that there is a Revit level here. Now, Revit level is pretty straightforward also as behavior. You have the name, the elevation, which is basically the height, computational height. If this is a structural level or architectural level, you see that when you see this structural here, it means that it can be considered in order for structural design, not only architectural design. And you see that normally structural properties in GG Revit components is always set to true. Okay, so whenever you see structural, if you are going to consider this from an architectural point of view, you might want to take a toggle, set it to false, and plug it into the structural input. Okay, I will do this because we are not interested in the structural behavior of our design. We are only interested in the architectural behavior. Okay, but nevertheless, you know that you can also emit or create structural levels. So the name. Well, normally I do recommend that you. It depends. It depends on you. Actually, in my Revit installation here, I have already defined a template. So when I open a new file, we will be going back and forth between Rhino and Revit. Okay, so forgive me this kind of jumps that I'm doing, but when you select a template file, I have created a template here, which is just changing the unit, the default unit, into meters. Okay, but when you open a standard Revit template, you will have the levels are named, are labeled with this kind of standard sequence, like level 1, level 2, level 1 being the ground floor. Okay, now pay attention to this because normally in Grasshopper, it's very common that sequences start from 0. I do recommend that you take into consideration what are the standards for Revit, not for Grasshopper. So we are going to create this level system exactly like it is already present and determined in Revit. So first level, ground floor, is level 1, not level 0. Okay. So if we want to give a name to this GG Revit level here, we must create a panel with with level, eventually level space. Okay, this is not mandatory because well, actually, let's see a smarter behavior, because also you see that if you want to create a panel with a string, character string, and space, you must further go inside the panel and place the space again, as it won't be stored. Okay, now it is stored. So if you want to avoid this, you can also create a panel with exactly the text that you want to use for the name, and then you take a concatenate component where you concatenate fragment A, which is going to be level, and then we need space, because there is a space here, and a progressive number that we can create with a series, right? So if I do this, remember that Grasshopper starts from 0. We don't want to start from 0. We want to start from 1. So let's take this, and I want to create a progressive structure here. I don't want to exaggerate. I'm going to create just 2 stories for this building. Okay, so I'm going to create count like set to 2, and I'm going to have 1 and 2. I plug them here, and as a result, I get level 1, level 2, but without space. But the concatenate component gives you the possibility to select a separator, which can be a space. So you see that this symbol appear with nothing in between. This is a space, and so we get level space 1, level space 2. So this is going to be the name. And as for the elevation, we need to define, for example, the height of each floor, which story. So I'm going to define this with a slider, more or less between something between. Well, actually, I'm not fully aware of the standards that you have in your respective countries. I will refer to Italy, for example. So in Italy, the minimum allowed height for an apartment is 2.17. Sorry. So this can be our minimum height, and you can range up to whatever you want. Okay. So this is going to be the floor height or the elevation. And what I want is another series where the step is going to be this one, and the count. And now we need to define levels, okay, not floors. So even if we have just 2 floors, we need to define ground level, first level, and top level. So they are 3 levels, okay? So actually, if you want, normally I would start from the definition of the amount of levels we need in Revit. So eventually I would create here a slider with 3. This is going to be the amount of levels that we need. And so we have 0, 2.7, 5.4. So these are going to be the elevations of our levels. And you see that it creates this plane, these horizontal planes here. So the representation, the geometric representation for Revit level are these horizontal frames that you see here. Okay, nothing more than that. The problem we have here is eventually that we now have only 2 names for our levels, while we need 3. And so I would recommend that you connect with an expression in the count of our series. You write down expression x minus 1, And so we plug the same slider defining the number of levels. So now we have, sorry, why I place this expression when I need exactly the same amount of names? My bad. So we have level 1, level 2, and level 3. Okay, so everything should work properly when we export things to Revit. And these are very important sliders if you are going to define a multi-story building, because this is actually defining the number of levels. Remember, this is not the number of stories or floors. This is the number of levels that you want to consider. And this is basically the floor height, or you can name it also levels elevation, but I do prefer to refer to the floor height, of course. So these are very important because changing these will affect the whole project. Okay, and now in this case, for example, you see that we have several frames. Okay, and we have this kind of situation where if we go into the front view, you see that actually these lines here are disconnected from the height, from the physical height of the levels. And we want to make this column end each time they find an horizontal level. Okay, so it's pretty easy actually. We can go once again into the intersection toolbar. This is a mathematical intersection because we have physical line and virtual orientations like these frames. So you go into mathematical and you will find the curve plane intersection. So you take all these curves here, and we must intersect them with these frames here. Now, this output here, even if you have this kind of preview, which are frames, these are not frames. So if I plug this into plane, you see that this thing here is actually recognizing them, even if you don't have the proper output. So this output here, this is something that has to do with how Grasshopper tries to smartly interpret the things that the user does. So plane should not be capable of recognizing these IFC strings, which are actually the output from this level. But as there is a geometrical output, which is only the frame, the curved plane intersection is capable of detecting that plane and using exactly that plane for the intersection. Okay. So you see that there are three output here: world XY, which is the horizontal frame at level 1, and then there is level 2 and level 3, which only have a different Z coordinate for the origin. Okay, and so we have these intersections that are coming out in a weird way. This is because we didn't graft the frames. So if we graft the frames, we have all the intersection at the different levels. You see that we are missing the upper intersection, but we don't care about that intersection. Okay, we just want to define where these columns are going to stop to end. Okay, so once we have these, we have the intersection points. So we can flatten these points also. So we have 20 intersection points, and we also have 10 intersection points. Now, why do we have 20 intersection points here instead of 10? Because we are intersecting 10 curves with 3 planes. And these intersections are actually detecting also the ground floor, because we are intersecting also with the level 1. We are actually intersecting with level 1, level 2, and level 3. So if these columns get extended more, you will also get the 10 upper intersection with the level 2. Okay, so you must eventually concentrate on the intersection that you want to consider. Okay, so in this case, for example, if I unflatten this, you will see that we have a huge data tree where you have several branches, but several branch levels. You would see that it is not only the last index of the branch that is changing. You see that it's 0, 0, 0, 0, and then 0, 0, 0, 1, 2, 3, 4, 5, etc. But the last branch is called 0, 0, 2, 9. This means that you can still separate the intersection by height. If we shift paths, You can also shift paths automatically by -1. If you do this, you have the same intersection, but they are now grouped into 10 intersections per layer. Okay, so what intersection you want to consider in this case? Well, let's do this in a non-parametric way. I can explode this data tree here, and now I only have the ground intersection in branch number 0, first and second layer of intersection. I want to concentrate on the first level. Well, sorry, level number 2. Okay, and so I want to define the connection lines, or basically the axis of our columns, starting from this intersection here at the ground level and reaching the intersection with the first floor. And so I want to use these as axis. And this allows to define the height of the columns in order for them to reach exactly the first floor. Okay, and you might want to adopt this strategy in order to define also some strange architecture. For example, we are using an attractor point in order to define the first order of columns at the ground level. And you can come up with whatever different approach in order to define the inclination of the columns at the first floor. So for example, in order to define the column at the first floor, we must have correspondence with the lower layer of columns, of course. We cannot shift columns from the lower floor, of course. So I would grab the endpoint and eventually create another STL line starting from this point. And I will use exactly the same floor height, which is this slider here, for defining the length of the first columns. And so we can use this. If you want to use the same column type, of course, you can blend or merge the same axis with the same ggRevit column. Okay, and we are defining a different method for creating column orientation at the first level. Depending on how good you are with Grasshopper, you can come up with several different strategies for handling this kind of complex situations. But nevertheless, this is a very simple approach. You can differentiate the structural, or well, actually the soon-to-come architectural column also, defining the rule that you want to adopt at each single floor of your building. Okay. So yes, that's what I wanted to point out as regard to columns. You see that when you use Geometry Gym tools, it's a complex set of parameters that you must take into account between Grasshopper behavior and techniques, and also Revit needs for defining properly the architectural or structural elements. So you can tweak these two different aspects for your definition and come up with a whole comprehensive set of geometries and parameters. Okay, so it's very nice to play with these tools. I will just reorganize this thing a little, and so we have this kind of final output, just in order to have a look to it. It is an IFC column, which has this kind of string. This is actually very important. So let me spend 2 minutes to describe this. And then eventually we will go for a short break. What's this thing? This is something that Rhino users normally don't know or don't take into account, because it's something that is already present in Rhino. So for example, if I draw, I don't know, anything, and I go into the details, you will see that there is this kind of thing here and this kind of thing here. Okay, this is an ID. Okay? So this is the way that a software understand what object you are taking into account, or in this case you have selected. Okay, and even when you if I take this for example, this curve, this line, and import it inside Grasshopper with a curve container, the way that Grasshopper is basically importing this line inside this component here is by its ID. So it's something that you don't take into account normally, uh, but this is the way that a software understands what object you are considering for a particular workflow. And this is also valid for the IFC definition. Now, this is very important, not inside Rhino Grasshopper, but when you import things inside Revit. Why? Because the first column that we are creating, column number 0, which depends on which axis is getting into this input, like first axis. So eventually we can create a curved container and plug these 2 wires here. And I would also recommend that you flatten this before inputting the relative content inside the axis. So we have this thing here, okay? What I'm interested now in evaluating, let me also, yeah, okay. So let's focus on these things here, okay? So what I want to do, I want to concentrate on which is the first item getting inside this component, and it's this one here. So this is the first column. And of course, this is the intersection between axis or grid line A with grid line 1, because it was the first grid line, horizontal grid line, and the first vertical grid line. But anyway, this is the line that we are considering. This is the first line, and the first line has a number 84, and this is the ID. Now, number 84 defines in a unique way this column inside the IFC file. But this is the name that is going to be given to this column inside Revit. Okay. Why is this important? Because if I, at a certain point, change things in Rhino, like this, for example, change the attractor point, this same column here will receive exactly the same ID. So when I import in Revit, this will be the name of that column inside the Revit file. Each time that I make some change in Rhino Grasshopper, that column will be given the same Revit ID. So when I re-import the IFC in Revit, the actual column will be substituted by the new version because it will have the same ID. So each edit or change that you make in Rhino Grasshopper, you can update Revit object by simply re-importing the IFC file. Now, this is something that has pros and cons, because eventually, in this case, for example, I want to update the column aspect, length, and orientation, but I don't want to update, I don't know, all the rest of the architectural elements that I have imported, because I want them to remain the same. If I re-import the IFC file, everything will be substituted. So if I import the IFC file in Revit and make some changes, and I re-import the IFC, all the changes get lost. Of course, there are ways of avoiding this kind of side effect, and we will see how this can be managed. But nevertheless, this is something that it's very useful when you want to make some design changes controlled with Rhino and Grasshopper techniques. Okay, so pay attention to this thing. One other thing is that remember that axes are defined by lines. Okay, so you can be tempted of doing something like this, joining curves. You see that here we have this line-like curve, so they are segments. If we join them, you will have one polyline per each column system. So you should have only 10 polyline curves. If you do something like this is going to get angry, because it doesn't understand polylines. It only understands the lines, okay? One thing that you might want to do in order to adjust this thing, because I'm considering right now that there is an orientation problem. I don't know if you already noticed this, but the orientation of the lower columns is not consistent with the orientation of the upper columns, okay? So in this case, there are ways that we are going to see that allow to change the orientation of the columns, or basically the cross-section in our case, okay? In order to come up with a consistent alignment of the cross-section throughout these different layers of columns. Okay, but this is something that we are going to observe later on. Is everything clear until now? Do you have any questions? You see how much work you must do for defining properly a single element right now, which are the columns, which is a pretty simple one. But this allows us to define native Revit element, native Revit element and properties, not only the geometrical aspect, but also the properties. Okay. Later on, I will also show you that each of the things that we have implemented here, for example, especially at the type level, have some attributes. For example, so you see material has attributes, and column type has parameters and attributes, and the column instance has also parameters and attributes. Okay, so everything here is set up to find the correspondence inside Revit. Okay, so that's why I consider this the better approach up to date to the interoperability between Grasshopper, Rhino Grasshopper, and Revit, because you are defining not only the geometrical aspect, but also, and most important, the non-geometrical aspect that is useful to produce schedule, quantities, and documentation. Okay, so is everything clear? Do you want to ask something? Do you have any doubts for what we saw? Guys, any observation?
Well, it's not a doubt, it's a question.
Yeah.
Is it possible, regarding the library of the profiles, to have extract the data of that library of profiles for example, an evolutionary solver to choose the best profile according to a certain law?
That's something that I already asked, because there are, for example, well, you know this, Bruno, because you were attending the Grasshopper architecture course last week. For example, when you use some structural plugin for Grasshopper like Caramba 3D, when you define a profile, there is also some components, some tools that allow to basically deconstruct the profile and get to its characteristic, so dimension and properties and so on. But in that case, for example, even in that case, that cannot be used for an optimization process, because the process in that case is that you define the profile like an eye profile, okay, with thicknesses and so on, and then you deconstruct this profile into its properties: width, height, thickness, thickness of the wings, and so on. Okay, so this is an output. You cannot use it for redefining this profile. Okay, it's a loop. Here it's the same, basically. Also, Geometry Gym still lacks this option, which is very important. I think this is more important for producing documentation than for optimization processes, because it's important to understand, okay, I am using an, I don't know, HD blah, blah, blah profile, and I want to understand what are the physical properties of this element, okay, in order to put this in documentation or whatever. So this is something that is not still possible in Geometry Gym tools, and it could be very useful. But if you want to use this for an evolutionary solver or some optimization tools that we already saw last week, I do recommend that you use the definition of a standard profile by parameters.
Okay.
So don't use the library. The library doesn't allow that kind of optimization process, but the standard profiles, they do. And consider also that there are, well, it's not exactly a comprehensive list of standard profile, but the principles are already here. So C, O, I, square, and T are already present. Okay?
Okay, thank you.
You're welcome.